Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. In this lecture, we will be solving some problems on Bayesian decision theory, discriminant functions, and the normal density that we have studied in last few lectures. So let us see this problem. We need to compute the Mahalanobis distance of x, which is given by a two-dimensional point 6, 2 from the distribution defined by the set of points given by this set. Okay, so if you will try to plot these points, then you can observe that if this is 1, 2, 3, 1, 2, 3, this will be minus 1, minus 2, minus 3, 1, 2, 3, and we can plot these points. So x equal to 1. So here we have 1 point, then 2, 1. So we have here 1 point, then 2, 2. We have here 1 point, then 2, 3. Then here we have 1 point, and then 3, 2. So this is our point distribution in the two-dimensional feature space. Okay, and from these points we can observe that it is something a circular distribution. Okay, now the question is asking to compute the Mahalanobis distance of point 6, 2. So 6 and 2. So somewhere the point is here, and we have to compute this distance. Okay, so we know that the Mahalanobis square distance is defined by r square into x minus mu transpose sigma inverse x minus mu. Okay, so here we have to compute the mean value of these points and the covariance of these distribution. So let us compute mean, which is mu equal to 1 plus 2 plus 2 plus 2 plus 3 divided by 5 and 2 plus 1 plus 2 plus 3 plus 2 divided by 5. Okay, so we have 2, 2. So this is the mean vector. Okay, now we can compute the covariance, which is given by 1 by 5 into xk minus mu transpose into xk minus mu, where k is from 1 to 5, because we have 5 points. Then we can put the value. So 1 by 5 is in common, then minus 1, 0, then minus 1, 0, plus, that means for k equal to 1, then we will calculate for k equal to 2. So it will be 0 minus 1, 0 minus 1, plus 0, 0, okay, then plus 0, 1 into 0, 1 plus 1, 0 into 1, 0. Okay, so when you will do all the vector multiplication, then you will obtain the covariance as 1 by 5 into 2, 0, 0, 2. That means after solving this, we will get sigma equal to 1 by 5 into 2002. Okay, and this is equal to 0.04000.4. Okay, and when we calculate the inverse of the covariance matrix, so here this is the diagonal matrix, and if we calculate the inverse of the diagonal matrix, then it is simply the 1 by the diagonal elements. So this is our inverse of the covariance matrix, which is equal to 2.500 2.5. Okay, now we can put the value of mean and covariance to compute the Mahalanobis square distance. So R square equal to, so the point X is given 6, 2. So 6, 2 minus 2, 2. So this is the mean, and we have to compute the transpose of that, and then sigma inverse. So 2.500 2.5, and then 6, 2 minus 2, 2. Okay, and when we will solve it, then it will be 4, 0. Okay, because we have the transpose, so it will become a row vector, then 2.500 2.5, and then 40. Okay, and we can solve it, then it will get 10, 0 and 4, 0, and we will get 40. So this is R square equal to 40. So this is Mahalanobis square distance. So what will be the Mahalanobis distance? R equal to root 40. Okay, so this is the our final answer for this question. Okay, then we have the next question based on the discriminant function, where we had to find the decision boundary, and we have the another question that if we will have the loss matrix, then where our decision boundary will move. Okay, so let us see what is the problem. So here we have, for a 2-class problem, the prior probabilities are p omega 1 and p omega 2, which is given. The class conditional distribution for upright x equal to small x, that means it is one-dimensional feature, that x has only single attribute. Okay, and we have given the class conditional probability distribution for class 1 and class 2. Okay, and then we need to compute the threshold boundary value xt, that means the equation of decision boundary, which gives the probability of minimum error. Okay, that means we have to apply the Bayes classification rule, and we will compute the decision boundary, which will classify the data samples, which will give the probability of error, which will be minimum. Okay, so here we have given parameter so we have given prior probability for class 1 as 1 by 4, prior probability of class 2 as 3 by 4, and also we have given the class conditional probability of class 1, which is the normal distribution with zero mean and unit variance. So this one is for class 1, and we have the class conditional probability for class 2 as the normal distribution with mean equal to 1 and variance is also 1. Okay, because this is sigma square, so sigma will be 1. In the same, sigma equal to 1. Okay, so if we attempt the first question, okay, so this is the case where the variance of both the classes are same. That means this is the case 1 that we have discussed in the previous class. So discriminant function can be defined as gix equal to minus 1 by 2 x minus mu divided by sigma square, okay, plus ln p of omega I. Okay, here we have considered the univariate, the probability density function. Okay, so our decision boundary will be g1x equal to g2x, or we can write g1x minus g2x equal to 0, the same thing. So it will be minus 1 by 2 x minus 0, because mean value is 0, and sigma is 1 square plus ln the prior probability of class 1, that is 1 by 4 equal to 1 by 2 x minus 1, because for class 2 we have mean value equal to 1 and the standard deviation 1 square plus ln prior probability of class 2. Okay, so just we need to solve this. Okay, so we can simplify it as minus 1 by 2 x square plus ln 1 by 4 equal to minus 1 by 2 x square plus 1 minus 2x plus ln 3 by 4. Okay, so just take this term to the right hand side and this term to the left hand side, and it will be minus 1 by 2 x square plus 1 by 2 x square plus 1 by 2 minus x, and it will be ln 3 by 4 divided by 1 by 4. Okay, just we are combining the two ln terms in a single term. So these two terms will be cancelled out and it will be minus x plus 1 by 2 equal to ln 3. Okay, 4 cancel out here. Then we'll have x equal to 0.5 minus 1.09. Okay, because ln 3 is equal to 1.09. Then we will get x equal to minus 0.59. So basically this is the threshold value, or we can say that this is the equation of the boundary. So because this is the univariate case, so in this case we will have the single point, which is the threshold value. Now let us solve the second bit. Here we have given a loss function where lambda ij matrix is given, and we have to find the threshold value for xt, okay, which is the decision boundary for minimum risk classifier. Okay, so here we have to apply the minimum risk classifier. So the second bit, given loss function lambda ij equal to 0, 1, 0.5, 0. Okay, and in case of the minimum risk classifier, the discriminant function is gix equal to minus r alpha I given x. Okay, so our decision boundary will be g1x equal to g2x. Okay, because it is a two-class problem, so we can write minus r alpha 1 given x equal to minus r alpha 2 given x. Then we can write minus lambda 1 into posterior probability of class 1 plus lambda 1 2 into posterior probability of class 2. Okay, minus, so this will be equal to minus lambda 2 1 into posterior probability of class 1 plus lambda 2 2 posterior probability of class 2. Okay, now we can write, that means we can put the values of the loss function in this equation, then we will get minus 0 into p of omega 1 x minus 1 into p of omega 2 given x equal to minus 0.5 into p of omega 1 given x minus 0 into p of omega 2 given x. Okay, then just this term will be 0, this term will be 0. Okay, so we have minus p of omega 2 given x equal to minus 0.5 p of omega 1 given x. Okay, so here we can cancel the negative terms, then we can put the posterior probability. So here we have ln p of x given omega 2 plus ln p of omega 2 equal to 0.5 into ln p of x given omega 1 plus ln prior probability of omega 1. Okay. So here we have minus 1 by 2 x minus 1 by 1 squared. So this is our px omega 2. That means the class conditional probability, log of class conditional probability. Okay. And then we can put ln of 3 by 4 equal to 0.5 into minus 1 by 2 x minus 0, that is the mean of the first class, divided by standard deviation, we make it square, then ln 1 by 4. Okay. So now we can write this expression as minus x square minus 1 plus 2x plus 2 ln 3 by 4. This will be the simplification of the left hand side, and right hand side we will have minus 1 by 2 x square plus ln 1 by 4. Okay. So now we will take x square as common, that means this term we can take on the left hand side, so it will be minus x square by 2, then minus 1 plus 2x plus 2 ln 3 by 4 and minus ln 1 by 4 equal to 0. Then we have to simplify this term, and it will be minus x square minus 2. Just we are multiplying with 2, so it will be 4x plus 4 ln 3 by 4 minus 2 ln 1 by 4 equal to 0, and then x square minus 4x plus 2 minus 4 ln 3 by 4 plus 2 ln 1 by 4. Okay. And if we will solve this constant term, then we will have the quadratic equation as x square minus 4x plus 0.378 equal to 0. Now let us solve the next problem. In a two-dimensional classification task, the feature vectors are generated by two normal distributions sharing the same covariance matrix, where the covariance matrix are given and the mean vectors are mu1, mu2 are given. Then we need to classify a vector 1, 2.2 according to the Bayesian classifier. So in this problem, we have given that these two classes sharing the same distribution, that means these two classes have the same covariance matrix, which is given by this equation. Here we have given the determinant and the inverse as well, and the mean of each class distribution is given, and we have to find that this feature vector will belongs to which class according to the Bayesian classifier. So here we have the given parameter mu1 equal to 0 0, mu2 equal to 3 3. Okay, and in this problem we don't have the prior probability, so we can assume p omega 1 equal to p omega 2 equal to 0.5. That means we are considering that both the classes are equally probable. Since both the classes are sharing the same covariance matrix and having equal prior probability, then we can write sigma 1 equal to sigma 2, and which is given 1.1, 0.3, 0.3, 1.9. Okay, and so sigma 1 equal to sigma 2, and it is 2, and sigma 1 inverse equal to sigma 2 inverse equal to 0.95 minus 0.15 minus 0.15 and 0.5. Okay, so in this case our discriminant function will be gi x equal to minus 1 by 2 x minus mu transpose sigma I inverse x minus mu. And we will here we don't have the prior probability term, because the prior probabilities are equal, so it will not contribute anything to make the decision, so it will not be in the discriminant function. So this is our discriminant function for this problem. So we will compute GIX for this given vector. Okay, so let us compute. So G1 X, so here X is 1, 2.2 transpose. Okay, so it will be minus 1 by 2 into 1 minus 0. Just I am subtracting the mean from X, so it will be this much, and then I am writing sigma inverse okay, and then 1 minus 0, 2.2 minus 0. Okay, so we can solve this. It will be 1 minus 1 by 2 into 1, 2.2, and then 0.95 minus 0.15 minus 0.15, 0.5, and 1, 2.2. Okay, so after solving, just multiply these two matrices, we will get 0.62, 1.06 into 1, 2.2. Okay, and it will be minus 1 by 2 into 1.44584, and it will be minus 0.72292. Okay, so this is the discriminant value for class 1. Okay, similarly we can compute the discriminant value for the class 2, and if we will calculate, then G2 x to 1 2.2 transpose, it will be minus 2.076. So in the same way we can do the calculation. So here already I have calculated, so I have written here. Okay, so here this is the discriminant value for class 2 for this given samples. So from these two values we can observe that discriminant value of this sample for class 2 is less than the discriminant value of this sample for class 1. That means what I mean to say, G2x equal to 1 2.2 transpose is less than, because minus 2.076 is less than minus 0.722. Okay, so this is less than G1x equal to 1 2.2 transpose. Okay, so that means we will make the decision in favor of G1, and G1 is the discriminant function for class 1. So x equal to 1 2.2 is classified to class 1. Okay, so this much for this lecture. Thank you.